Okay, so this brings us to semiconductors and band theory. So band theory grew out of molecular orbital theory. It's a more comprehensive model for metallic and covalent solids. So atomic orbitals of atoms in a crystal combine and are delocalized over the entire crystal. So in a sense, a crystal is like a giant molecule. It's a covalent solid. It's covalently bonded all the way throughout, and the orbitals overlap. So when the atoms combine, and they form these molecular orbitals, the lower energy bonding orbitals are the ones that are occupied, and the anti-bonding orbitals are the ones that are going to be empty. When we get more and more atoms in this giant molecule, the difference in energy between the bonding and the anti-bonding orbitals gets smaller and smaller and smaller until it's so small that it doesn't really matter anymore. So let's look at that. So lithium, right? Lithium has one valence electron. So here we've got one valence electron. When you put two lithium atoms together, you get an anti-bonding orbital and a bonding orbital. And each of those atoms has one valence electron, and they're both going to go into the bonding orbitals. When you put three together, let's skip that one because that one doesn't make a lot of sense because an odd number, what the heck's going on there? Let's skip over to this one, 4. So now we've got 4 atoms coming together. We've got 2 anti-bonding, 2 bonding orbitals. And these are going to get closer and closer together. And as we get to a large number, like a mole of lithium atoms, now we have empty orbitals. Those are the anti-bonding orbitals. And the occupied orbitals are lower in energy, but there's almost no difference between them. So notice as we're going from 1 to 2 to 3 to 4, the electrons always fit in the bonding orbitals. They don't have to go into the anti-bonding orbitals. So the anti-bonding orbitals are empty. This is called the conduction band, and this is called the valence band. The valence band, because that's where the valence electrons are. So any questions yet? So the electrons become mobile when they move from the highest occupied molecular orbitals, the valence band, into those slightly higher energy empty molecular orbitals called the conduction band. So electrons can move. It requires a little bit of energy, but not much. In metals, there's really no gap in energy between the valence band and the conduction band. Electrons can easily move up into the conduction band, and then they're mobile. So metals are good electrical conductors because the electrons can get into the conduction band and move. Thermal conductivity goes hand in hand with this because those mobile electrons can transport thermal energy throughout the entire crystal lattice. And so it will conduct heat. I think I've got it. Metals conduct heat and electricity. So I think of it a little bit like this. So think of this as a highway. And the valence band is full. There's a lot of electrons in the valence band. So this is a crowded highway, right? The conduction band is like the high occupancy vehicle lane, right? Or maybe going over onto the shoulder, right? It's open, it's empty, right? So why don't we go drive on the shoulder? Why don't you drive on the shoulder?
It's illegal.
Because it's illegal. Because if you get caught doing it, there's going to be some consequences, right? There's a cost to doing that. Some people do it occasionally. It's not a good idea, but they do it. So in a conductor, the energy gap was like the risk, the potential cost of driving on the shoulder of the crowded highway. You get over there and you can just take off, right? There's nobody ahead of you. You're good to go. Whereas over here, you're just like stuck in stop and go traffic. You can't move. If there's no penalty, then the electrons can go up there and conduct. Over here in an insulator, there's a large energy gap. There's big consequences if you're caught driving why can't I remember the name of that part of the road? The shoulder. Driving on the shoulder.
That would require more energy, or a lot of substantial energy you could be able to get to the conductor.
Yeah, so for this insulator, it would require a large amount of energy for an electron to move up into the conduction band. And so it doesn't. It doesn't. In between, we have semiconductors. There's a small energy gap. And so they don't conduct electricity very well, but they can. And so their conductivity is going to depend on things like temperature. If you heat a semiconductor, it is more conductive than when it's cold. So we've got limited conductivity, and you can control it. Any questions? So the band gap, that difference in energy between the valence and the conduction band, decreases as you go down any column of elements. So if we look at group 4, we've got carbon, silicon, germanium, tin, and lead. What did we learn about the trend in metallic character? As you go down group 4, do they become more metallic or less? They become more metallic. And one of the characteristics of metals is that they conduct electricity. So we see that as we go down group 4, the band gap decreases. So diamond, this particular allotrope of carbon, has a band gap of 5.5 electron volts. It is an insulator. Diamonds don't conduct electricity. Graphite does, but we're talking about diamonds here. And as you go down, silicon and germanium have smaller band gaps, but still a significant, and so they're semiconductors. And then we get down to tin, has a small enough band gap that it's considered a metal, and lead has no band gap at all. So as you go down, they become more conductive. What happens is that as you increase the atomic radius, you get that reduces the overlap between orbitals on neighboring atoms, and that reduces the energy difference between the bonding and the antibonding orbitals.
Would element 114 count as well?
Yeah, so element 114, which is below lead, we would predict that that would be electrically conductive and would be a metal. But it's a man-made element, and it's so unstable that we can't even get a mass on it, or we don't even know what color it is, because you can't make enough of it to look at. So we can control the conductivity of semiconductors by adding impurities to them. So these are called doped semiconductors. Put small amounts of impurities that either add extra electrons, so putting extra electrons into the conduction band, or removing some electrons and causing electron holes in the valence band. So there are N-type and P-type semiconductors. An N-type semiconductor has extra electrons. So silicon is a semiconductor. It's in group 4. If we throw a little bit of phosphorus in with the silicon, phosphorus has 5 valence electrons compared to silicon's 4. So in this doped semiconductor, we have some extra electrons. They have to go into the conduction band because the valence band is full. So now in the semiconductor, we've got some electrons that are always in the conduction band, and so we have better conductivity for the semiconductor. It's called an N-type semiconductor because what's carrying the charge is those extra electrons. The electrons are negative, and so this is called an N-type semiconductor. Add extra electrons. A P-type semiconductor, so you can take silicon again, and this time add some gallium. Gallium only has 3 valence electrons. So when you've got this combination now, because of the gallium, you have some holes some empty spaces in the valence band. And so what can happen is the electrons in the valence band can move into the holes. And so it's not as free, perhaps, as going into the shoulder of the road. But if you just took a few of the cars out of the traffic jam, things would begin to move, right? So the holes can move. And so holes act as positive charges. And so this is called a p-type semiconductor. It's deficient in electrons. Silicon chips, which, there's a bunch of them in the cell phone in your pocket, in your calculator, in the screen. Well, no, not the screen, but in the projector and all the electronic devices. Silicon chips have millions of p-n junctions. So these are areas where one side is a p-type semiconductor, the other side is an n-type semiconductor. And these can act as diodes. A diode is something that allows current to flow in only one direction, or they can act as amplifiers, which takes a very small current, amplifies it into a large current, and that gets into a whole nother area of electronics. But material science is pretty important there, because the reason we have these small cell phones, which, back in the 70s, even a computer that occupied the size of the basement of this building couldn't even do a small portion of what your cell phone can do, and it fits in your pocket. It's really pretty amazing. So this sort of a question could show up on that exam. Which element would you dope into germanium to create a p-type semiconductor? Well, what does p-type mean? Does a p-type have extra electrons, or is it short electrons? It's short because p means positive. We're looking at positive holes moving. So it must have fewer valence electrons than germanium. So if we find indium and tin and arsenic on the periodic table, there's tin and indium and arsenic, and we're doping germanium. So tin has the same number of valence electrons. That's not going to do anything. Arsenic has one more. That would create an n-type semiconductor. So it's indium. It has one less valence electron, and so that would create a p-type semiconductor. Any questions? Go home and tell the people in your life. We talked about dope in chemistry. Doping of elements.